Good morning. Welcome to the Swan Analytical USA webinar series. My name is Dominic O'Donnell. I'm the Marketing Director at Swan Analytical USA. In just a moment, I'll introduce you to our speaker, Randy Turner. But first, I want to familiarize you with our webinar software. You should be seeing both our slide deck and what's called a GoToMeeting control panel towards the upper right of your screen. By default, you should be receiving the audio through your computer speakers, although if you're dialed in, you can click on the phone call option to get your audio that way. Currently, we have all attendees muted to prevent background noise and distractions. We do still want to hear from you if you have any questions or feedback. And again, we can use the GoToMeeting control panel for that. Please type your questions and comments into the dialog box and send that off to me. I'll be monitoring the incoming questions and we'll address them at the conclusion of the webinar. Our speaker this morning is Randy Turner. Randy Turner has been the Technical Director at Swan Analytical USA since 2012. Prior to that, he served as corporate chemist and as a plant chemist at Southern Company for over 33 years. Over the years, he has authored numerous papers and been an active member of EPRI and ASME, including time as chairman of EPRI's Cycle Chemistry Program. We're pleased today to have Randy share some of that experience with you. Randy, take it away.
Thank you, Dominic. We're very excited to talk to you today about steam purity and its implications. So what we're going to talk about today is a brief introduction on steam purity and things of that nature and why it's important. We will talk about degassed conductivity and the methods of measurement. We'll talk briefly about cation exchanger design and how that impacts cation conductivity as well as degassed conductivity measurement. Then we'll describe some of the measurement and design features of the Swan degassed conductivity monitoring system, and then review some case studies, and then summarize what we've talked about. In today's power generation, with all the renewables, there's tremendous pressure to reduce startup times on our traditional units as well as our combined cycles. Cation conductivity is a key decisive measurement parameter for steam purity as well as condensating feed water. And today the focus is on providing fast, accurate cation conductivity values to facilitate fast startups. To have a fast and accurate cation conductivity, it's greatly influenced by the design of the sampling and monitoring system. But the key message is steam purity is critical to protect the assets. So why is steam purity so important? Well, you have a new steam turbine or a reconditioned steam turbine that's in pristine condition, has very high reliability and performance. However, operating over the years, we have chemistry upsets, you have contaminants entering the steam cycle, and those can form deposits, which leads to pitting on the steam turbine. And those pits lead to cracking, which can result in very expensive repairs and even catastrophic failure. The reason steam purity is so important is you can have corrosive contaminants such as chlorides and sulfates, as well as some other species that can form deposits on the steam turbine throughout various areas of the steam turbine. And those corrosive deposits lead to pitting during outage periods when the steam turbine is exposed to very humid, oxygen-saturated air. And when you bring the unit back online with the mechanical stresses, you can have cracks form between those pits, and it can lead to corrosion fatigue failure of the blading and the discs in the phase transition zone of the LP turbine. You can also incur stress corrosion cracking of the blades and discs in the phase transition zone of the LP turbine. So the risk of turbine corrosion requiring expensive repairs can be significant if your steam purity is not acceptable and meeting OEM and industry guidelines. So, where do these steam purity limits come from? Well, the OEMs such as Siemens, ASTM, Toshiba, GE, as well as organizations such as EPRI, IOPS, and VGV. Therefore, values above normal operating limits may be tolerated for short periods of time, particularly during startup. However, the greater the deviation, the shorter the allowable duration operating outside the normal operating limits.
So we're going to launch a quick poll here. We want to get your feedback. We feel that degassed conductivity is a very critical parameter, but we'd like to know what you're seeing. What do you feel is the most important parameter when monitoring steam purity? Please go ahead and select one and hit send. See, we're starting to get some responses. We'll leave this open for just a few more seconds here until we get a representative response. Over half our attendees have voted. I'll give it just a few more seconds here. Okay, it's a pretty good response, and let me just share that with you. What we've seen, well, looks like we may need to follow up with some webinars on silica and sodium, but it looks like we've got the right topic for today, with 71% of the people responding to us agreeing with us that degassed conductivity is as important a parameter as you're going to come across when monitoring steam purity. So we'll go ahead and close that up for now. And back to you, Randy.
Thank you, Don. Okay, what you see in this table is the impact of different species on cation conductivity. The typical cation conductivity limit by OEMs as well as organizations like EPRI for normal operation is 0.2 microsiemens per centimeter. And what you see in the table is a list of common contaminants that can be in the steam. And the values beneath each contaminant is the concentration in ppb of that specific contaminant required to yield a cation conductivity of 0.2. And it can be a number of contaminants that is driving the conductivity, or it can be dominated by one particular contaminant, such as carbon dioxide during startup conditions or during periods of high air leakage. The thing about carbon dioxide with respect to the steam turbine is it's not corrosive to the steam turbine. Therefore, it's not an issue that would warrant restricting steam to the steam turbine during startup. However, when your concentrations of carbon dioxide are significantly elevated, it can drive the conductivity to values of 1 microsiemen and higher, thereby masking the presence of more corrosive species such as chlorides and sulfates, which are very corrosive to the steam turbine. Therefore, it's important to be able to get a more accurate measurement of the cation conductivity due to the presence of species such as chloride and sulfate. So when you're operating and your cation conductivity is 0.2 microsiemens, you have this question in the back of your mind. Is it due to the presence of 16 ppb of chloride, or is it 46 ppb of CO2 or carbon dioxide, or a combination thereof? What you see here are the OEM and industry steam purity limits for various parameters, such as organizations such as EPRI, IOPS, and the OEMs that you see listed here. And the typical cation conductivity limit for normal operation is less than or equal to 0.2 microsiemens. And then you look at silica is typically less than 10, sodium and chloride less than or equal to 2, sulfate as well. And many of you manufacturers accept degassed cation conductivity, at least for startup and commissioning, and now many of the OEMs accept degassed cation conductivity for normal operation. What you see in this table is Siemens steam purity limits for the various parameters listed, and it's specifically identifying the action levels for the various parameters listed. And you see it goes from action level 1 to action level 4, and it shows the range of the various parameters listed, in which would identify which action level your steam chemistry is currently operating. Now, during startup, Siemens recommends that the steam purity should be in action level 2 and trending downward, which is identified by the green lettering. So turbine startup with respect to Siemens guidelines should occur within action level 2, as I said, with a downward trend. Now, let's talk a few moments about degassed cation conductivity. As I mentioned earlier, most OEMs accept degassed cation conductivity for startup and commissioning, but many of them now accept it for normal operation. Degassed conductivity analyzer removes only carbon dioxide. It doesn't remove the corrosive anions such as chlorides and sulfates, or even organic acids that may derive from using organic treatment chemicals. According to Steve Schulder, EPRI Program 64 Manager, steam conductivity should be measured by degassed cation conductivity and be less than 0.1 microsiemens per centimeter, independent of the treatment. Now, let's talk about steam purity limits. Cation conductivity alone could lead to delays based on OEM as well as technical organizations such as EPRI. I've seen cation conductivities during startup as high as 1.5 microsiemens in my career, and it is predominantly being driven by carbon dioxide. The degassed cation conductivity provides a more accurate, more complete picture of your steam purity with respect to cation conductivity. Therefore, utilizing degassed conductivity eliminates the guesswork on carbon dioxide's contribution to your cation conductivity. Let's talk about methods of degassing your sample to measure degassed conductivity. Nitrogen sparging is one method, and it consistently removes around 70% of the carbon dioxide. Reboiling. In 2004, Dr. Nigel Drew did some research on degassing samples, and he evaluated the methods available at that time: nitrogen sparging and reboiling, and gas transfer membranes, which we'll talk about in a moment. And during his study of the available technology, the nitrogen sparging removed 70% of the CO2, and the reboiling removed 28 to 58%. And the reason for that variability in the reboiling is because the technology at the time did not take into consideration the actually boiling point temperature of the water, which is driven by the barometric pressure. So as the barometric pressure changes, the actual boiling point temperature changes, affecting the efficiency of the CO2 removal by the reboiler. And then the third method he evaluated was, as I said, gas transfer membranes, which remove between 40 and 63% of the CO2. And this report is available in PP Chem. Let's take a moment to talk about cation exchangers. What you see on the left is a traditional resin column cation exchanger, whereby the sample flows from the top to the bottom, and then a vented cation exchanger on the right. You see the sample flow in and goes through the resin, and on the traditional column, then it flows to the conductivity cell to measure the cation conductivity. The design on the right, the sample comes in, flows down, and then it flows up through this little funnel and out past the cation conductivity sensor, but it most importantly has the air vent to allow air that is accumulated in the cation exchanger and is entrained in the sample, particularly during startup, to be expelled, thereby greatly reducing its impact on the cation conductivity. What you see in this graph is a comparison of cation exchangers. A traditional cation exchanger, and what you see here in the graph is a conductivity measurement of the high pressure steam of a combined cycle in blue and the condensate cation conductivity in red. And this is after measurement with a traditional cation exchanger. Now what you see are the exact same samples where the cation conductivity is measured utilizing a vented cation exchanger. And you can see a tremendous difference, particularly initially. In fact, it takes over 2.5 hours for the traditional unvented cation exchanger conductivity to trend down to the levels of the vented cation exchanger. So it greatly impacts your cation conductivity measurement as well as the degassed cation conductivity measurement. Looking at the sample profile as it transitions through a cation exchanger, your incoming sample, of course, you have your water, you have various contaminants, and you're alkalizing, or the chemistry that you're feeding for pH control, in this case, ammonium hydroxide. It flows through the cation exchanger, and of course, the incoming sample is typically pH value of greater than 9. It flows through the cation exchanger, then your sample pH is typically less than 7. Of course, you have water, and then it removes the cations, therefore you're left with anions such as chloride, carbonate, formate, and acetate. Now, if you're using degassed cation conductivity, downstream of the degasser, what you have remaining is water, chlorides, formates, and acetates. It removes the carbonates and CO2.
So before we move on to the next portion of our presentation, where we talk specifically about Swan's solution to measuring degassed conductivity, we wanted to have a quick poll. Randy showed you some images earlier on about the kind of problems that can result from issues with steam purity, and we want to just get a feel for what we have in the audience today. What types of problems have you seen in monitoring your steam purity? If you could go ahead and click on whatever one of these is the level of problems that you've seen. So got about a third of our audience responding so far. We're just going to keep this open for a little bit more. Okay, over half of you have responded. A couple more seconds here. And we're going to go ahead and close that up and share the results with you. And I had a little bit of a side bet with Randy. I said, Randy, anybody that's going to take a half hour out of their day just to hear us talk about degassed cation conductivity, those are diligent enough people that they would have never let their system get to catastrophic failure. And that's what we've got here. But as you can see, everyone's had, except for a few folks, they've seen the problems that we talked about, the pitting that requires corrective action. And we know that if you're monitoring it closely, hopefully you can get ahead of the game on this and not reach those last two categories. So Randy, I'm going to hand it back to you, and if you could go ahead and walk us through what the Swan AMI degassed cation conductivity can bring to the game.
Thank you, Dominic. Okay, now what I want to take a few minutes and describe our complete Swan AMI Degassed Cation Conductivity. It's a complete monitoring system for the automatic continuous measurement of 3 conductivity values as well as a few other things. It measures the specific conductivity. It measures your cation conductivity after the cation exchanger. And then it measures the degassed conductivity after the reboiler for your degassed cation conductivity. It also calculates your sample pH by differential conductivity and calculates the concentration of your alkalizing agent, in this case ammonia. It is designed to remove 90 to 95% of the CO2 as compared to what you saw on the earlier slide of 28 to 58% on the evaluation performed in 2004 by Dr. Drew. And the reason we can remove 90 to 95% is we employ something that is critical, which is precise boiling point temperature control, which we'll talk more about. What you see here is our degassed conductivity monitoring system. Of course, you have the transmitter and the specific conductivity cell, which when the sample enters the monitoring system, the first thing that is performed is a measurement of the specific conductivity. Then the sample flows through the vented cation exchanger and past the cation conductivity sensor. And what you see on the right is the degasser control system. And here you see the heater, the heat exchanger, and the degassed conductivity sensor. Now, looking more at the Fluidics Overview, the sample enters at O, flows past the specific conductivity sensor, then it enters the vented cation exchanger, flows down to the bottom, flows up through this pathway past the cation conductivity sensor. Once it exits the cation conductivity sensor, then it flows through an integrated flow sensor so that you know what your sample flow is, which is very important, which I'll talk about in a moment. Then it flows into the heat exchanger where the incoming sample cools the boiled sample. Plus, it's also preheating your incoming sample to make the reboiler more efficient. Goes through the heat exchanger into the reboiler where it is heated up to approximately within 0.5 degrees centigrade of the boiling point temperature. It exits the reboiler, goes to the heat exchanger, is cooled down to 40 to 50 degrees centigrade, flows through the degassed conductivity sensor, and then to drain. Now, the importance of this flow sensor, it's to protect the instrument so that during startup, you typically have very intermittent sporadic sample flow. Typically what happens with reboiling systems is it loses sample flow during startup. The sample boils to dryness, then the sample flow is reestablished and that cold sample hits that heating element and damages it or destroys it. Since we measure the sample flow at a specified flow value of less than 3 liters per hour, the reboiler is powered down to protect the reboiler. Once the sample flow is greater than 3 liters per hour, it repowers the reboiler and begins measuring the degassed conductivity again. The design of the system is ASTM 4519-94. As I said, since the incoming sample cools the boiled sample, there is no need for an independent cooling water source, which makes your installation less costly and also provides a greater level of protection because you could lose your cooling water and then that sample is not cooled, which could damage your instrumentation. The electronic controller for the reboiler controls the operating temperature of the reboiler to maintain 90 to 95% removal of CO2. Every 6 hours, it determines the boiling point temperature and controls within a half a degree centigrade of that boiling point temperature. It also has 2 barometric pressure sensors in the electronic controller, so that if the barometric pressure changes sufficient to affect the boiling point temperature, it recognizes it and it activates the boiling point temperature determination process. Therefore, when measuring degassed conductivity, temperature is critical, and you have to precisely control that temperature near the boiling point temperature for removal of 90% or greater carbon dioxide removal. Looking at some of the measurement design features, again, we mentioned earlier, it measures the specific, the cation and degassed conductivity, which you see displayed on the screen right here. It will calculate the pH and the ammonia concentration, which is displayed on the second screen. It also displays the sample temperature and the flow at the bottom here. Again, it automatically powers down or shuts off the reboiler with loss of sample flow to protect the reboiler. And it's designed to consistently remove 90 to 95% of the carbon dioxide. It also has the capability of calculating resin consumption with an alarm to alert the user that the resin is nearing exhaustion. The value of the degassed conductivity is it removes carbon dioxide so that the presence of more corrosive species such as chloride, sulfate, acetate, and formate can be monitored more effectively to eliminate the masking by the carbon dioxide. It can provide much faster startup times if you restrict steam to the steam turbine due to conductivity or other chemistry parameters. In that case, it increases your revenues, it reduces your startup costs, and it is also a valuable troubleshooting tool because you can use it to determine, is the root cause of my elevated steam or condensate feed water cation conductivity, is it due to carbon dioxide or something more corrosive such as chlorides and sulfates? So it eliminates the guesswork. We're going to go over a few case studies here to show you the impact of measuring degassed cation conductivity. And what you're going to see here is some commissioning data from a HRSG. It's a tri-pressure air-cooled HRSG, and the goal is for the cation conductivity of HP steam meeting the limit to admit steam to the steam turbine. It's being treated with ammonia and carbohydrazide. So what you see is the red line is the cation conductivity and the blue line is the degassed cation conductivity. You can see there's a tremendous differential between the cation and the degassed cation conductivity. And what you see at this line right here is they begin injecting carbohydrazide, which once it reaches the temperatures sufficient to break down the carbohydrazide to hydrazine and carbon dioxide, you see an increase in the cation conductivity as well as a slight increase in the degassed cation conductivity. And this is due to CO2 being driven off of the carbohydrazide. At this point, they increase the drum blowdown and you see a significant decrease in the cation and a slight decrease in the degassed cation because the degassing unit is removing most of the CO2. And at this point, they begin feeding ammonia, and you see the impact on the cation conductivity and degassed conductivity. This is a little bit busy, but what you're looking at here is startup of a combined cycle unit. It's a cold startup, and we're going to be comparing the cation versus the degassed cation conductivity. And the lines in the graph that are important is this line. This is the megawatt load. This green line, which is the cation conductivity. And this blue line here, which is the degassed cation conductivity. And this red line here is the 0.5 microsiemens limit in action level 2 for Siemens, at which point when the degassed cation conductivity is below that, you can admit steam to steam turbine, assuming the other chemistry parameters are also within action level 2 and trending downward. So you see there is a significant difference in the degassed cation conductivity versus the cation. And here's where they synchronize the gas turbine to the grid, and you can see the degassed cation conductivity went well below the 0.5 limit, then slight increase above it, then quickly dropped down to 0.5 and less. Whereas the cation conductivity was as high as 2 microsiemens, and after a couple of hours or longer, the cation conductivity was still above 1 microsiemen. And you may wonder why the degassed conductivity increased to the value of the cation conductivity here. Well, just to show that the degassed conductivity was working properly and measuring accurately, the reboiler was powered off. Therefore, it's no longer degassing. As you can see, then the conductivity matched the regular cation conductivity because it's no longer degassing. So what is the practical impact of degassed conductivity on your operation? Well, here's 4 different case studies, 3 of which were cold starts and 1 was a warm start. In this first column here, it's the time from synchronization of the gas turbine start to when the cation conductivity was less than 0.5 microsiemens. The center column is time from gas turbine start to the time in which the degassed cation conductivity was less than 0.5 microsiemens, which, as you can see, was significantly less. And the third column is the time differential between the time at which the cation versus the degassed cation conductivity was less than 0.5 microsiemens. And as you can see in case 1 on the cold start, degassed conductivity less than 0.5, almost 4 hours sooner than the traditional cation. Cold start 2 is almost 2 hours. Cold start 3, it was almost 4.5 hours. And then even on the warm start, it was almost 2 hours sooner to reach less than 0.5 than the traditional cation conductivity. So, utilization of degassed cation conductivity can reduce startup times as much as 62 to 70%. So, in summary, degassed cation conductivity is a valuable tool for troubleshooting. Degassed conductivity can reduce your startup time significantly. And not all degassed systems are the same accuracy, and that's dependent upon the design.
All right, well, thank you, Randy. And as I say, we'll be sending a thank you email to you and a request for a survey rating today's webinar. And we hope to see you on our next webinar. Well, thank you for attending and have a really great day. Bye-bye.